Right, so we are down now to our last topic, and it's graph theory. Now, when you've got a chance, just have a look at page 101. I think it's a good idea to read the glossary, just to remind us, because graph theory, it really is easy, but there's a million things to remember. It's very different to whatever we've done in maths. I will just pick through a few things that we need for today. And one is that really maybe the most important thing about graph theory is that you've got vertices and edges. That's the main thing, really. And yeah, that's it. Now, last year, we did a lot of what we dealt with Eulerian problems, or Eulerian circles, or paths. I don't remember what, you're going to just read it, okay? But it was Eulerian. And what is Eulerian about? It's about edges. So if you remember, we had the Chinese postman, right? It was all, this guy had to go through all the different paths. It didn't matter, you know, about if he hit all these guys, all the vertices, but he had to hit all the edges. This year is all about Hamiltonian paths, which means we're not interested about the edges. I mean, obviously they play a part, but we're gonna have to go through all the vertices. So the way they say it, Hamiltonians remember about hubs, you know, hubs, little thingy. And what we are aiming for, we're not going to deal with it today, it will be next time, is what you call the traveling salesman problem. Okay? So I will just quickly mention it now, just so you know where we're going. A guy, he's a salesman, he has to go through all the cities. Yeah, he has to go through all the cities and then come back to where he started from, and he wants to take the shortest route. Okay? So we need to hit all these places, and he's going to take us, we're going to develop a couple of algorithms how to actually calculate that. That's it. Okay? Are we all right? Okay. So what we're going to do today, we're going to learn the algorithm to find minimum spanning tree. Now, what does that mean? So imagine we've got these, this is the graph. And by the way, I'll just say here that if these two lines, these two edges cross, it doesn't mean that they really cross. Yeah. Okay? It's not that we can go from here to there. This is like from C to E is 9, from F to D is 12, but you know, they could be actually in 3D, you know what I mean? And in fact, these things don't have to even be spatial. So, and I explain it using an example. So what is a minimum spanning tree? We're basically trying to find the shortest path that will connect all the vertices. You don't have to go through all of them, but it's like we need to, you know, shortest spanning tree. I think I kind of explained it. So here's the example. And I did think about two examples. One is Woodridge students. So you've got this whole, Woodridge spice. Okay. So imagine each vertex is a person. Okay. And each one of these edges is a chat. Conversation between two people. So we want to find out how many chats, and maybe the number could be how long that chat takes. So between different people, it takes longer. So what you can ask yourself, what we're trying to find is, what's the least amount of time needed to spread the spice everywhere? Yeah. Okay? It doesn't mean that he has to also go to here, but they all have to be connected like a spider web. You know, okay? You understand? Mm-hmm. Right. Another example that I thought, especially for you, Arne, because I heard you're a really good script writer. So that's what I've heard. Okay? So we can mathematically define a good script like this. I really thought about it. So imagine these are characters in the play. You're all drama guys, okay? These are all characters. And, well, it's not going to work. Maybe work with the numbers. But each edge is, what is an edge going to be? Maybe a relationship. Yeah, character. Between the characters, a father, a mother, a lover, a friend. Okay? And then, so the minimum spanning tree will be like the minimum web inside of a play. Because, you know, obviously they all have to be interconnected somehow. You can't have just one person on his own that just walks around, nobody knows him, right? Yeah. So the minimum spanning tree will be like the minimum relationship for a certain play, and then you can say, then you can using that baseline, you can kind of say, oh, this is a very rich script because it has many, many relationships. Maybe you can even talk about an ideal, mathematically ideal script where you don't want to have too much. If there's too many relationships, then the audience doesn't know what's going on. So anyway, this is just some thoughts I had, on a Friday night or something. Okay, anyway, so how do we do that? So the answer is there are two algorithms, and we're going to learn them today, and they're really easy. Okay, the first one is called cruise score. That's obviously the guy who came up with this idea. And I'll just tell you what we're going to write. It's step 1. Okay, we're going to find the shortest path, or add the shortest. I'll get rid of that. Add the shortest edge. What do we call it? Yeah, edge to the spanning tree. Okay, so I'm gonna go as we write it. We're gonna do it. Okay. So, what is the shortest one? 3, I think so, yeah. So we're going to do a squiggly, okay? Right, that's step 1. Step 2, add the shortest remaining edge to the spanning tree. I'll write it to, should we call it spanning? Well, I'm just not going to say it. Just add the remaining shortest edge, unless it creates, what do they call it, a circuit, provided it does not make a circuit. Yeah, unless it makes a circuit. What does a circuit mean? You'll see in a second. Okay, so which one is the next one? 4. Okay, and then step 3, repeat step 2 until all vertices are joined, and we're going to add something to it in a minute. Okay, so let's just carry on and we see what does that mean in the circuit business. So which one is the next one?
5.
Okay, but if I add 5, I don't really need to add 5, because look, by 3 and 4, C, B, and A are connected already. So there's no point in adding that 5. It doesn't add any extra value. You understand? Okay, so this is like an extra dimension in our script, we don't need it, okay? So I did step 1, I went to step 2, okay, so I'm not going to put 5. So we're going to go back to step 2. So which one is going to be the next one? 6. Yes, now if there's, I won't write it down because it's like, well, I should read. So in step 2, I'm going to also add, if there's more than 1, then choose. Randomly choose. Then randomly choose 1. Okay, so, there's no point. 6 or 6, just choose 1. Doesn't matter. Okay, and then which one is the next one? 7. Okay, so we always have to see that we didn't make a loop. Circuit is like a loop.
Oh, so you don't include the other
6? No, you're right, the 6. Yeah, you're right. So we don't cancel that 6, unless it was going to create a circuit. So you're right, this 6, and then we're going to put that 7. That's not creating a loop, right? So, okay, then we put a 7, and then, okay.
But 8 creates a loop.
The thing, okay, 8 will create a loop. Can we do anything? Can we do 9?
Yeah.
9 will
also create a loop. Okay, so there's one thing we didn't mention here. Where do we know to stop?
When you're back at the beginning.
Well, not really, because we don't need to go back to where we came from. All we got to do is make sure everyone's connected. Is there one that is not connected? To someone. Look, they're all connected.
Oh, you mean like a thing on its own?
That's it. So think about, we don't have anyone in the play that just nobody talks to because nobody really knows. They're all connected. That's the minimum spanning tree. That's it. Okay? So, now, this is a small graph. I mean, there's only what? 1, 2, 3, 4, 5, 6. Okay? So it's quite easy to see that they're all connected. But if we have 10, 20, it's going to be more difficult. So it would be nice to have an indication how many edges do I need? How many edges do we have here? 5. 6 vertices.
So you get one vertex.
It's always going to be one less, right? Think about it. If I have 2 vertices, well, I need 1. If I have 3 vertices, well, I need 2. Okay, so it's always, so let's write it down somewhere. Here, how do I know to stop? Repeat step 2 until all vertices are joined. Let's write down. How do you know when to stop? Let's just write it. For graph with n vertices, we need n minus 1 edges to make, what do we call this? Spanning, minimum spanning tree. Minimum spanning tree. Okay, it's very easy, isn't it? Okay, I'll pause here. So, yeah, Olivia is asking correctly. So what was the answer? So really the question is, whatever this can be. This could be like the distance between city, or it could be length of cables between computers that can create some kind of system. So they might ask you, what's the minimum length? So then we just need to add them. 4 plus 3 plus 6 plus 7 plus 6. That's it. But the real reason why we're doing this, you only understand next lesson. We're going to use this minimum spanning tree to do something in the traveling salesman. Okay? So that is one method. We have another method, which I'll discuss now. I'll just clear some space. Yeah, so now the next method, next algorithm is called Prim's algorithm. Another dude. Okay? And where should I start? Okay, so it's very similar but a little bit different. First of all, we have to start with a vertex. And it will be interesting. Maybe we can do it later if we're getting different results from wherever we started from. And I think, yeah, you will. Yeah, you definitely will. Well, I don't know. Let's see. but for now, let's just start with B. Okay? Why? Because they did. Later on, we'll start with a different one and see if we get something else. So the idea here is that we start with any vertex, and step 2, we find the shortest edge that join this. This vertex is on the tree now, so we're creating the tree. So we're finding the shortest edge that will connect us to another vertex which is not on the tree. So in this case...
Oh, the tree that you worked out.
Yeah, so this is... No, we haven't got a tree. We're recreating a tree. So I should have said this is the same graph, but I'm starting from scratch. Okay? The main difference with... You'll see there's a couple of differences, but with Prim, we always start... We decided where we want to start, and we start with B. So I'm looking for an edge, which is the smallest, which will connect me to a vertex that is not in the tree. Right now, only B is on the tree. So any edge that I will choose will be fine. So which edge should I choose? Obviously the shortest one. So which one? The 3. It's still the 3. So it starts really the same, but you'll see in a second it will look a little bit different. Okay? So right now, B and C are on the tree. The rest are not. Then it tells me, okay, I need to go to the next, add it to the tree. If there's more than one possibility, choose one. That's the same as before. So in other words, don't get stuck. Because, remember, all these are algorithms, programs that we write for computers. If a computer needs to decide between 6 and a 6, and you don't tell them just choose one, they'll just get stayed forever, So we got to be a bit more clear with them. Listen, the computers. Now, step 3, repeat step 2. That should be step 2 until all the vertices on the tree. Right, we don't have all the vertices on the tree. So we're looking for the shortest edge that will connect us to another vertex that is not on the tree. So which one will that be?
The 5.
Well, you got a 4.
We're still doing from B.
Yeah. Oh, right. I see. Yes. Okay. So, yeah, that's a good thing. So, right now, the tree that I have is B and C. Now, it doesn't mean that because now I'm in C, I have to go from C. I can still go, so that's a very good point on it, okay? It doesn't, I can go from B or from C. So 4 is smaller, so I'll go go to A now. Now I've got A, B, and C on the tree. Okay? Now what will be the next one?
The 6.
The 6. But you remember last time I had 2 6s. In fact, according to Crew School, you could choose anyone. But here, our algorithm will not allow us this 6 because he's not connected. You know, I need to either go from C, or from B, or from A. Do you understand what I'm saying? It's more, you know, the way they use it in the textbook, they say, remember Prim is prim and proper. It's a little bit more like, it's like you see pictures of crystal growing and it's like,
Yeah.
so this is what it is like this. It's not, Crew School was like, right, 3, 4, 6, 9, 7. No, that's different. Here we have to grow from something. Does that make sense?
Yeah.
Okay? Alright, so the next one will be, well, we're not 5. Why are we not 5?
Because it joins one
Creates the thing.
Okay, so in Crew School we said 5 will create a circuit. Here we don't have that problem in the circuit, but it says we need to go to a vertex that is, where does it say? Go to the shortest edge that joins a vertex on the tree to a vertex not on the tree. So, see, yeah, not on the tree. Now if I go the 5, well, C is already on the tree. Does that make sense?
Yeah.
Okay, so we're going to go that one. Right, what's the next one?
The 7.
The 7, yeah, because E is not on the tree yet. F is on the tree now. Okay, so we're going to go 7.
6.
And now is the 6. Yeah, so you see how it was slightly, the result is the same result. Okay, the Crew School gave us also those 2 6s, but in Crew School I'll go from this 6 then to that 6. Okay, where Prim, I can only stretch out new little feelers, yeah, from where I'm at. Okay, so it's going to be that one.
That one.
Yeah, and then by that time I know to stop because I have 1, 2, 3, 4, 5 edges on 6 vertices, so I know to stop. Okay? Right, I think what we'll do, let's try do the same thing but not start from B. And see if we get, because I'll be honest with you, I don't really know. Is Prim and Crew School always give you the same answer? I don't know.
Surely they have.
So I think
Let's
it
try.
would.
Let's try.
Yeah.
So, just to finish up, we had a little discussion here and we figure out that, at least on this simple graph, whether you use Prim or Crew School, you will get the same, result. It doesn't matter where you start from Prim. So let's say if we start with D, in Prim, so then the shortest one will be 6, and then we'll do a 7. And then obviously it's all the same. But that does not, I'm still not 100% sure what happens if you have more complicated graph. Where is it going to matter where you're going to start with from? I don't really know. Okay, you can find out. Okay, that's it here. Short lesson. On Thursday we're going to do traveling salesman. Bye bye.